Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of capacitance. So in this revision session we're going to look at how to answer examination questions on A-Level Physics Paper 2. So if we're successful and we learn in our revision session today, we should be able to answer A-Level Physics examination style questions for capacitance. You should have an understanding of what you know for A-Level Physics capacitance topic, and then understand what topics in the capacitance module you need to improve upon for AQA A-Level Physics. So how should you prepare for revising in this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In that left hand side section, write down any working out or answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side section, write down any bits of information which you find useful or any hints and tips on answering questions from the revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, in terms of how you should revise for A-Level Physics, the first step you should be doing is learning the key facts. So use revision guides, class workbook, student prep notes and a textbook to learn the key ideas of the course. You may wish to make mind maps or to write out notes yourself. Secondly, test yourself. Use the Caboodle e-learning platform, Seneca, student knowledge checkers to quickly test your knowledge. You may wish to do this from cue cards. And then finally, practice with examination style questions. So use exam prep books, homework books, study books, additional workbooks to answer exam questions and mark your own work. And you may wish to download your own exam past papers to do this. So in terms of how you should be revising your A-Level Physics, there are three steps. Step 1, learn the key facts. Secondly, test yourself. And then thirdly, practice an examination style questions. Now, in terms of the questions we'll cover in this revision session, there'll be three types of question we'll look at. There'll be general check questions, the basic questions designed to probe your understanding of the key concepts of the topic. Secondly, are checkpoint questions. These are more challenging questions designed to place your own knowledge and understanding of the topics into different applications and contexts. And finally, assessment points, past paper exam questions which mimic the type of questions found in public examinations. So with that being said, let's now have a look at some capacitance questions. The first question says, a 470 microfarad capacitor is connected across the terminals of a battery of EMF 9 volts. Calculate the charge on the plate of the capacitor. Secondly, calculate the potential difference across the terminals of a 2200 microfarad capacitor when it has a charge of 0.033 coulombs on its plates. And then finally, calculate the capacitance of a capacitor if it stores a charge of 2 coulombs when there is a potential difference of 5000 volts across its plates. So pause the video now, then unpause the video when you want to go through your answers. Right, so this is using that key equation that capacitance is equal to charge over potential difference. So if we have a look at this particular equation, we can rearrange it and we can make charge the subject. So we can say Q equals CV. We turn micro into farads, so it'll be times 10 to the minus 6. So we get 4.2 times 10 to the minus 3 coulombs. We rearrange this one to make V the subject. V is Q over C. Once again, we turn micro into the normal farads by times 10 to the minus 6, and we get 15 volts out. Then finally, we say capacitance is charge over potential difference, so we work it through and we get 4 times 10 to the minus 4, which is 400 microfarads. The next question says, a student inserts 2 bare copper wires into a lump of wet clay. The clay is dried out. The student suggests that he has made a capacitor. Explain whether this is correct. The next question says, the charge stored by a capacitor connected to a 12 volt battery is 2.4 times 10 to the minus 5 coulombs. Calculate its capacitance in farads and then microfarads. A capacitor stores a charge of 30 picocoulombs when the potential difference across is 3.2 volts. Calculate the charge stored in picocoulombs when the PD is increased to 8.7 volts. Then the capacitor of capacitance 200 microfarads is connected to a 10 volt supply. Calculate the number of electrons removed from the positive plate of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to understand what the definition of a capacitor is. Yes, it is a capacitor because it consists of 2 metal electrodes separated by an insulator, which is what we define our capacitor to be. The next one, once again, we use the equation capacitance equals charge over potential difference, pop in the values, and we get 2 microfarads. In this next one, we then say, well, looking at the equation, if we've got a constant capacitance, we can say that Q is directly proportional to V. So when we work it through in the terms of ratios, we can say it's 81.6 picofarads. And then the last one here, what you can do is use Q equals CV, work it out to be 2 times 10 to the minus 3 coulombs. Remember, microfarads turns into farads by times 10 to the minus 6. We then work out how many electrons we've got by taking our overall charge, dividing by the charge of an electron, 1.6 times 10 to the minus 19 coulombs, and we get 1.3 times 10 to the 16 electrons. The next question says, a capacitor of capacitance 0.010 farads is connected to a 1.5 volt cell. Calculate the number of electrons delivered by the cell to the capacitor. Then an uncharged capacitor of capacitance 1500 microfarads is connected in a circuit. The current in the circuit has a constant value of 80 microamps. The capacitor is charged for a time of 60 seconds. Firstly, calculate the charge and the PD across the capacitor after a time of 60 seconds, and then sketch a graph of PD across the capacitor against the time over a period of 60 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, once again, Q equals CV, work it through, divided by the charge of an electron, 1.6 times 10 to the minus 19, we get 9.4 times 10 to the 16 electrons out. In this next one, we've got to use an equation from electricity. Charge is equal to current times by time. So when we turn micro into amps by times by 10 to the minus 6, so we work out our charge to be 4.8 times 10 to the minus 3 coulombs. We can then say V equals Q over C to get 3.2 volts. Now, if you look on here, how will the potential difference go against the time? Well, you'll notice that it'll be a straight line graph through the origin, and you'll get a value of V equals 3.2. It's 60 seconds because from the answer to our previous question. The next question says a 22 microfarad capacitor is charged by using a constant current of 2.5 microamps to a PD of 12 volts. Calculate the charge stored on the capacitor at 12 volts, the time taken. A capacitor is then charged by a constant current of 0.5 microamps to a PD of 5.0 volts in 55 seconds. Calculate firstly the charge stored, and then secondly the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, again, we're using Q equals CV. So we will put them in. Remember, micro turns into the farads by times 10 to the minus 6. So we get 2.64 times 10 to the minus 4 coulombs. Again, we can say Q equals IT. So therefore, T equals Q over I. We've already got Q from the question. Okay, and we've got I from the question. So we can work it through. Remember, we worked out Q in our previous answer. So we can pop it through and we get 105.6 seconds. In this second question, once again, Q equals IT. So we know I, because we can work it through, be 0.5 times 10 to the minus 6, times by the time in seconds, 55, so you get 2.75 times 10 to the minus 5 coulombs. And then we can work out the capacitance by saying C equals Q over V. We worked out Q in our previous question. We know the value of V from the information given, it's 5, so we get 5.5 times 10 to the minus 6 farads. The next question says, a capacitor is made from a plastic bin bag sandwiched between two sheets of aluminium foil 60 centimeters times by 30 centimeters in size. The bin bag is 0.080 millimeters thick. Plastic has a relative permittivity of 4.0. Calculate the capacitance of this capacitor. Then the capacitance of a parallel plate capacitor is 8 picofarads. State and explains capacitance when the separation between the plates is doubled, then the area of overlap between the plates is halved and their separation is also halved. Then a capacitor is made from two circular plates of diameter 20 centimeters. That are separated by an insulator. The insulator has a relative permittivity of 4.0 and a thickness of 1.2 millimeters. The capacitor is connected to a 6-volt battery. Calculate the maximum charge stored by the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one, you've got to use the parallel plate capacitor equation. So that is C equals the area times by ER, E0 over D, where ER is our relative permittivity and E0 is the permittivity of free space, which is a constant given to you on the equation sheet. You pop in all the values given to you in the question. Now remember, you have to turn centimeters into meters, and you have to convert millimeters into meters as well. So you can pop those through as shown in the working out on the screen. Pop in our values, and we get 80 nanofarads. The next one, you can see from the equation above that C is directly proportional to 1 over D. So therefore if D is doubled, well, C will then half, so it's gone from 8 picofarads to 4 picofarads. Once again, we can see from the equation above that C is directly proportional to A, but C is directly proportional to 1 over D. Now, because A and D will both change by the same magnitude, the same factor, they'll cancel each other through, so we get 8 picofarads. This next question again, we're going to have to use our equation from above, the parallel plate capacitor equation, but this time we're going to have to work out our area. Now we can see that the area is going to be just for one of the plates, so we do pi r squared. Now we've got the diameter in centimetres, so we convert that to a radius, which is 10 centimetres, and then convert it into metres, so 0.10 metres, pop in all the values, work it through, and we get 9.2 times 10 to the minus 10 farads. We can then work out our charge stored by saying Q equals C times by V. We've just worked out the capacitance, we know the voltage because it's given in the question, we get 5.6 nanocoulombs. The next question says the diagram shows a capacitor constructed from two plates separated by glass. Firstly, calculate the area of one of the capacitor plates, state your answers in meters and then in standard form, and then the relative permittivity of glass is 3.7, calculate the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the trick you're going to have to do is to work out the area is to times the length by the breadth, but these values are given in millimeters and you've got to put them into meters. So you pop them into meters, multiply them together, and we get 1.1 times 10 to the minus 3 meters squared. Then the second one, we'll once again use our equation here. So we can see it's going to be the parallel plate capacitor's equation. So it's 3.7 times by the permittivity of free space times by the area we just worked out, divided by the separation in meters, which is 0.002, so you get 18.4 picofarads. The next question says a 120 microfarad capacitor is charged through a 1 mega ohm resistor using a power supply of a constant output of 3.0 volts. The initial PD across the capacitor is 0. After a time equal to 1 time constant, calculate the PD across the capacitor. Then for the circuit in this previous question, calculate the PD across the capacitor at a time of 3 minutes. Then an uncharged capacitor of capacitance C is charged through a resistor of resistance R using a battery of EMF V0. Derive an equation for the time taken t for the PD across the capacitor and the resistor to be the same. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to use our equation for a charging capacitor. So we say that V equals V0, which is the starting, which is the EMF, or the output of the power supply. Okay, multiplied by 1 minus e to the power minus t over RC. Now remember, RC is a time constant, so after 1 time constant, t is going to equal RC. So it's going to be RC over RC, which is going to cancel through to be 1. So therefore what we're going to get is we're going to say it's going to be 3 times by 1 minus e to the power minus 1. Pop that through and we get 1.9 volts. This next question, we can see what our time constant is because we've got R and we've got C, so we can work out the time constant to be 120 times 10 to the 6. Okay, so minus 6, my apologies, because it's microfarads times by 1 times 10 to the 6 because it's mega ohms, so we get 120 seconds. So again, we're using our equation here where we know RC to be 120. We know the time to be 180 because we don't work in minutes in physics, we work in seconds. We then pop in all the values and we get 2.3 volts. And then here we're using this equation, we can work it through here. Now it's important to note that we can say that when you work it through the laws of logs, you'll see a half equals e to the power minus t over RC. Pop in all the values through. Now remember, to get rid of an exponential from e, we do natural log, so therefore log of a half will equal log e to the power minus t over RC, so that will cancel through. Bring that power term down to be just a normal term, so it's minus t over RC. We work it through, so t therefore equals log 2 or 0.69 RC. The next question says a trainee electrical engineer has constructed a flat plate capacitor. The dielectric between the plates has a permittivity of 40 times 10 to the minus 12 farads per meter. The capacitor is connected to a 6 volt DC supply. Calculate the charge stored on the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question there's a lot of different equations we're going to have to use. Firstly, we're going to use the parallel plate equation because we're being given the relative permittivity and the separation and the areas. Remember the dimensions for the area. Now remember they're given all in millimeters, so you have to convert them. So we use our equation C equals ERE0 over D. We work it all the way through and we get the capacitance out to be 14.4 times 10 to the minus 12 farads. We then say Q equals CV, and we want to work out the value of Q. So we pop in all the values. We know V is equal to 6, so it's 86.4 times 10 to the minus 12 coulombs. The next question says, a 220 microfarad capacitor is charged at 2.0 volts, then discharged through a 100 ohm resistor. Calculate the maximum current in the circuit and the maximum charge stored by the capacitor. Then calculate the time constants for these circuits. C equals 0.010 farads and R equals 1.0 kilo ohms, and then capacitance is equal to 4,700 microfarads and resistance is equal to 1.5 mega ohms. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how to work out the current? Well, again, use your equations from electricity. I is equal to V over R, so therefore it's going to be 2 over 100, so it's 2.0 times 10 to the minus 2 amps. Therefore, charge Q equals CV. Well, we know the capacitance because it's given in the question, so we're going to convert 220 microfarads to 220 times 10 to the minus 6, multiply it by our value for the potential difference there, 2, so we get 4.4 times 10 to the minus 4 coulombs. Now in this next one, what can we do? We can therefore say T equals RC. That's our equation for a time constant. So T equals RC, so it's 0.01 times by 1,000 because kilo turns into ohms by times it by 10 to the 3, so it's 10 seconds. And this next one, we turn micro into farads by times 10 and 10 to the minus 6. We turn mega into just ohms by times it by 10 to the 6. The 2 will cancel through and we'll get 7.05 times 10 to the 3 seconds. The next question says, a fully charged capacitor is discharged through a resistor when the switch is closed. Firstly, calculate the time constant for the capacitor. Secondly, when the switch is closed, the capacitor begins to discharge. When T equals 0, the voltage across the capacitor is 12 volts. Calculate the voltage across the capacitor after 20 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we know T equals RC. So we pop in all the values. You've got R from the question. Remember, kilo turns into ohms by 10 to the 3. You got given capacitance in the question. Micro turns into farads by times 10 to the minus 6. So you pop it through to get 7.26 seconds. Then in this next question we can say, right, well, V equals V0 e to the power minus T over RC. We know RC is the time constant, so it's 7.26. We know that V0 is the EMF or the power source voltage, so therefore that is going to be 12 because V0 is the maximum possible voltage the capacitor could have, so therefore that is 12. So therefore you pop in all the values. T is 20 seconds, so you get 0.763 volts. The next question says, in the 18th century, a scientist called Gordon made the first device that used electrostatic forces to produce continuous motion. A demonstration of the principle of Gordon's device is shown. A light conducting sphere of radius r is suspended from an insulating thread between two parallel metal plates. A large potential difference V is applied between the plates. There is an electrostatic force on the sphere when the sphere is charged. The capacitance C of the sphere is given by C equals 4 pi epsilon 0 r, where r is the radius of the conducting sphere. The sphere is charged by touching it onto one of the plates. The plates are a distance d apart. Calculate the electrostatic force exerted on the sphere. V equals 4,500 volts, D equals 5.0 centimeters, and R equals 3.5 centimeters as well. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question you're going to have to use all the equations given to you. So you're given the equation for capacitance and you know that you've got R and you know 4 pi epsilon 0. So how do you work it through? So you say, right, in this first one, 4 pi epsilon 0 times by R. In this instance R is 3.5 times 10 to the minus 2 because it's centimeters into meters. So we get our answer to be 3.89 times 10 to the minus 12 farads. We can then say Q equals CV, so therefore we can work out Q. We've just worked out C. We know V is 4,500 volts, so you get 1.75 times 10 to the minus 8 coulombs. We then know from the electrical fields module that a capacitor is a uniform electrical field, so its uniform electrical field strength is V over D. Pop in those values. We know D to be 5 times 10 to the minus 2 meters, so it's 9 times 10 to the 4 volts per meter, and therefore F equals E times by Q. That is the electrostatic force equation. So you pop in those values and you get 1.58 times 10 to the minus 3 newtons. The next one says a 1000 microfarad capacitor is connected in series with a 6 volt battery, a switch, and a 22 kilo ohm resistor. Calculate the charge of the capacitor after 10 seconds and the potential difference across the capacitor after 10 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, we're looking at how much, because it's charging up, because it's connected with the battery. So we're going to use the charging equation, that Q equals Q0 times by 1 minus e to the minus t over RC. Now we can work out what Q0 is, because it's the maximum possible charge, therefore its capacitance times by the maximum possible potential voltage or potential difference, which is that of the power source. So you can pop in those values. We've got the capacitance of the capacitor, we've got the EMF of the power source or the potential difference of the voltage, work it all through, pop in all the values, okay, in the equation. Now remember, we can work out what our time constant is, because we can say time constant equals RC, and therefore we can pop in all the values, we get them through, we get 2.2 times 10 to the minus 3 coulombs. This next question, we can just use the equation V equals Q over C. We've got the capacitance in the question, you've just worked out Q, so therefore you can work it all through and we get 2.2 volts. The next question says a 1000 farad capacitor is charged by connected in series with a 9 volt battery and an 18 kilo ohm resistor. Calculate firstly the maximum current, then calculate the time for the charging current to half, then calculate the time constant of the circuit, and then estimate the time for the capacitor to be fully charged. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, it's all about thinking what information you're given. So the maximum current is going to be equal to V over R. So therefore, what is V? Well, it's the maximum current, so therefore it's the maximum potential difference, which is going to be the EMF of the power source. You divide it by the resistance of the circuit. It's 9 over 18 times 10 to the 3, because kilo turns into ohms by that method. So you get 5 times 10 to the minus 4 amps. The next one, you've got to remember the equation. The time taken to halve is going to be 0.69 times by RC. So therefore it's 0.69 times by the time constant, which is going to be R, which is 18 times 10 to the 3, times by 1000 times 10 to the minus 6. So therefore it's 12 seconds. Whilst the time constant itself is just RC, so you can work it through to be 18 seconds. Now you've also got to remember the fact that we assume a capacitor to be fully charged or discharged after 5 time constants. So you multiply your time constant by 5, so it's 90 seconds. The next question says, a 1000 microfarad capacitor is charged by connecting it in series with a 4.5 volt battery and a 47 kilo ohm resistor. Calculate firstly the maximum PD across the capacitor, then calculate the charge on the capacitor 10 seconds after the circuit is completed, and then calculate the time for the charge stored to reach 63% of its maximum value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the maximum PD across the capacitor is going to be the EMF of the power source, which is 4.5 volts. Now, to work out the charge on the capacitor 10 seconds after it's been completed, we've got to use our charging equation. Q equals Q0 times by 1 minus e to the power minus t over RC. Popping all the values through. Remember, Q0 is CV0, so you know V0 is the EMF, 4.5 volts. You know C is the capacitance in farads, so you convert microfarads to farads. Pop in all the values, and we get 8.6 times 10 to the minus 4 coulombs. Now, this idea of to reach 63% of its maximum charge, that's the definition of a time constant. It's the time it takes to reach 63% of its maximum charge during charging, or to 37% of its starting value during discharge. So you just work out the time constant by doing RC, so you get 47 seconds. The next question says, State what is meant by a capacitance of 37 millifarads. Then a capacitor is made up of two parallel plates which are separated in air by a distance d. A cell of negligible internal resistance is connected across the capacitor as shown. Switch S is closed and the capacitor becomes fully charged. While S is still closed, the plate separation is reduced to d over 2. State and explain what happens to the magnitude of the charge stored by the capacitor. Then explain how the charge is conserved when the plate separation is reduced. Then S is now open. The plate separation is increased to d. State and explain how the energy stored in the capacitor changes during this process. Then explain how energy is conserved when the plate separation is increased as described in question 1.4. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to learn what the definition of capacitance is. It's how much charge is stored per unit volt. So this would be 37 millicoulombs stored per unit volt. In this next question, we know our equation to be C equals AE0 ER over D. So therefore capacitance doubles in voltage because of the fact that the separation has been reduced to D over 2. So therefore it's an inversely proportional, so capacitance will double. We know voltage stays the same in this question, so Q equals CV. So if C is doubling, Q is doubling. Now charge will be conserved because an equal number of electrons is removed from the positive plate as is added onto the negative plate, so therefore overall the capacitor is uncharged. Now in our next question here, okay, you know that the charge will stay the same because the capacitor is isolated, so the charge can't flow. So therefore if the capacitance halves and we use our energy stored in the capacitor equation, the energy will therefore double. And then how will this energy be conserved? Because the gain in stored energy is provided by work being done into actually pulling the plates into a further separation away from each other. The next question says, show that the capacitance of an isolated conducting sphere of radius r is given by the formula C equals 4 pi epsilon 0 r. Then figure 24.22 shows two identical conducting brass spheres of radius 10 centimeters mounted on insulating stands. Sphere A has a charge of plus 5.0 times 10 to the minus 8 coulombs and sphere B is uncharged. Calculate the potential at the surface of sphere A, then calculate the energy stored on sphere A. Sphere B is brought up to sphere A and is touched so that the charge is shared between the two spheres before being taken back to its original position. Calculate the energy stored in each sphere and then suggest why there is a change in the total energy of the system. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know the following. We know that V, okay, is going to be equal to Q over 4 pi epsilon 0 R, where V is our potential. That's an equation from the electrical fields module, which you can use because a sphere is going to produce a radial field. We then also know that Q is going to be equal to this 4 pi epsilon 0 times by V times by R. We know therefore C is Q over V. So what we can do is we can work it all through. The V's cancel through, so it's 4 pi epsilon 0 epsilon 0 times by R. To work out our potential, again, we're using that electrical potential for a radial field. V equals Q over 4 pi epsilon 0 R. So you can pop in all those values and you get 4,500 volts. Therefore, the energy stored is going to be the work done is equal to a half QV. Again, that's an equation from the electrical fields module. They're very closely linked. Pop in all the values and we get 1.1 times 10 to the minus 4 joules. In this next one, we know that the new charge on each sphere, because they've been touched, so therefore they will share that particular charge equally, so it'll be 2.5 times 10 to the minus 8 coulombs. Our new potential is therefore going to be 2,250 volts because we're sharing the voltage originally, so therefore it halves. So therefore the new energy found on each of them is a half times by QV. We've got a new value of Q, we've got a new value of V, so we can work it through and we get 2.8 times 10 to the minus 5 joules. Our next question says, okay, why is there a change in the total energy of the system? Because energy will be lost or dissipated to the surroundings to heat the spheres, and that'll happen as the charge moves from one area to another area. The next question says, define the term capacitance of a capacitor. Then figure 24.23 shows a circuit which can be used to measure the capacitance of a capacitor. The reed switch vibrates backwards and forwards at a frequency of 50 Hz. Each time it makes contact with A, the capacitor is charged by the battery so that there is a PD of 12 volts across it. Each time it makes contact with B, it is fully discharged through the resistor. Calculate the charge that is stored on the capacitor when there is a PD of 12 volts across it. Then calculate the average current in the resistor resistor, and then calculate the average power dissipated in the resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, learn the definition of capacitance. It's the charge stored per unit volt across the capacitor plate, or per unit potential difference. In this next one, we use our old capacitor equation. Q equals CV. You've got a value for V, 12. You've got the capacitance, worked it through. So therefore, you can say to be 67 times 10 to the minus 6, working it through. So it's 800 microcoulombs. We then say I equals Q over T. In the question for Q, we've just worked out what previous question, we've worked out what Q is. We know the value for time given before, because the time for one oscillation is 1 over the frequency, so it's 1 over 50, so you get 0.04 amps. And then we can work out the power dissipated, because P equals V over I, where V is the average potential difference. So you work it through, so it's going to be half of 12 because it's the average, so therefore it's 12 times by 0.04, so it's 0.24 watts. Our next question says a 0.10 farad capacitor is used in a circuit as a backup in case of a short interruption in the mains power supply. The PD supplied at the circuit is 230 volts. How much charge can the capacitor store? Explain why a capacitor would not be a good source for powering a portable media player. Then a 12 volt potential difference is applied to a capacitor. The capacitor stores 144 microcoulombs of charge in each plate. What is the capacitance of the capacitor? So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, once again, use that capacitor equation. Q equals CV, so it's 0.1 times by 230 is 23 coulombs. Then it wouldn't be a good source, because you're going to have to think about the media player would have to be very large to have enough power, so it wouldn't be able to be portable. Or alternatively, you could say you could only power the device for a short period of time, but you've also got to remember that the capacitor loses charge and therefore loses current it can apply to the circuit over time, so you wouldn't have a constant power output. Now in this next one, you can say capacitance is equal to charge over potential difference. We know what the charge is. It's 144 times 10 to the minus 6. We divide it by the potential difference of 12 to get 12 microfarads out. The next question says, for the airspace parallel plate capacitor shown, calculate the PD when it stores 25.5 microjoules of energy. Then explain why the capacitor stores energy when a PD is applied across to the plates. And then finally, a group of scientists claim that they've developed a new dielectric that enables the above capacitor to store 1,000,000 times more charge and energy for a given PD. Explain what further steps must be taken by the scientific community and the industry before this new dielectric can be used in devices and sold to the public. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, again, you've got to be able to work through, okay, what your value is going to be, okay, and you can work it through here. Sorry, I'll put on the wrong there, force acting per unit charge. So how you'd work it through is you would work out the value of Q by doing C, by working out, the value of C by doing C is equal to AE0 ER over D. Now remember, convert the values given from centimeters into meters, or millimeters into meters. So you can work out your area by doing 8 centimeters times by 8 centimeters, but into meters, and then you can work through your capacitance overall. You can then use that to then work out what the energy is by using your equation of E equals a half CV squared. So therefore, what you can do is rearrange, make V the subject, and then you can pop in the values to work it out. Now explain why a capacitor stores energy when the PD is applied across its plates. Well, the PD leads to a charge imbalance between the plates, so therefore there'll be electrostatic energy, or electrical potential energy between those two plates. And then how can you ensure that devices must be safe and sold to the public? So you're going to repeat the experiment, do it very reliably, repeat by other research groups, other people, to make sure the results are reproducible, test for safety, test for the lifetime, look at the cost effectiveness, look at the environmental impact, and check for a big issue with capacitors, which is the idea of charge leakage, charge going between those two plates of the capacitor. The next question says, a physics student wishes to construct a capacitor that will store 31 nanocoulombs of charge when connected to an 8-volt power supply. He carries out some calculations and determines that placing 2 square aluminium plates of side length 21 centimeters at a distance of 0.10 millimeters from each other will be suitable. Determine whether this capacitor setup will store the required charge. Then state how the student could increase the charge stored without changing any of the dimensions of the capacitor or the power supply to it. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you're using a parallel plate capacitor equation. So you use that parallel plate capacitor equation, convert centimeters and millimeters into meters, and work the capacitance through. So it's 3.9 times 10 to the 9 farads. You can then say charge is equal to CV. You know what V is going to be because it's an 8-volt supply. So it's 31.2 nanocoulombs. You then write a statement concluding your findings, which is that it would store the required charge. Now in this next one, what would happen? How could you increase the charge without changing the dimensions? Well, place a dielectric between the two plates, as that will automatically increase any charge. The next question says, when a 470 microfarad capacitor is discharged through a fixed resistor R, the PD across it decreases by 80% in 45 seconds. Calculate the time constant of the capacitor resistor circuit. Then a 680 microfarad capacitor is charged fully from a 12-volt battery. At time t equals 0, the capacitor begins to discharge through a resistor. When t equals 25 seconds, the PD across the capacitor is 6 volts, so that the time constant discharge is 36 seconds. Then a capacitor of capacitance 330 microfarads is charged to a potential difference of 9 volts. It is then discharged through a resistor of resistance 470 kiloohms. Calculate the potential difference across the capacitor 60 seconds after the discharge has begun. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using V equals V0 e to the minus t over RC, and then we're going to work out what R is. Now, the trick is that you can see that you can link in V0 in V by saying, well, V is equal to 0.2 V0 because it's lost 80% of its charge by that point of V, so therefore it's lost 80% of its voltage, so therefore it's 0.2 V0. It's 0.2, it's 20% of its voltage of what it was at the start. Pop in all the values, rearrange, make RC the subject, use your maths to convert the exponential power there into a normal term by using a natural log, so we get 28 seconds out. In this next question, very similar again, we use V equals V0 e to the minus t over RC because it's a discharging circuit. We then say V, which is the voltage at the time, is 6. The maximum voltage is 12, so you can pop all those values in. We know t equals 25, pop in the values through, work out the maths, get rid of that exponential term, and then we get RC equals 36.1 seconds. And then in this next one, what I would do for this one is V equals V0 e to the minus t over RC again, because we've got our potential difference at the start, which we know to be 9. We can pop in all the values and work it through, converting kilo and micro into those actual values, and we get our answer to be 6.11 V. Now, the next question says, a 250 microfarad capacitor is fully charged from a 6-volt battery and then discharged through a 1 kilo ohm resistor. Calculate the time taken for the charge on the capacitor to fall to 37% of its original value. Then calculate the percentage of the total charge remaining on the capacitor after 0.7 seconds. Then the charging voltage is increased to 12 volts. Explain the effect that this has on the total charge stored in the capacitor, the capacitance of the capacitor, and the time taken to fully charge the capacitor. Then a fully charged 320 microfarad capacitor is discharged through a 1.6 kilo ohm resistor. Calculate the time taken for its voltage to drop to half of its value when it was fully charged. So pause the video now, then unpause the video when you want to go through your answer. Hopefully in that first question you've realised that the time taken to fall to 37% of its starting value is a time constant when it's discharging, so T equals RC. Remember, micro turns into farads by times 10, working it through that way, times 10 to the minus 6, and kilo goes into ohms by times it by 10 to the 3, so we get 0.25 seconds. This next question, we can say Q equals Q0 e to the minus t over RC. We're working out our percentage, So we're basically going to find Q over Q0, our percentage work through. We know RC, because we've just worked it through to be 0.25 seconds. We know T to be 0.7 seconds. Pop in all the values, work Q over Q0, so we get it to be 0.06, so therefore 6% of the initial charge left on here. Now you should be able to be aware that the total charge doubles because Q is directly proportional, so V is directly proportional to Q. The capacitance will not change because it's a fixed property of a capacitor. That's a very important principle. If you don't change the dimension of the capacitor, the capacitance stays fixed, and then the time taken to charge doesn't change, because what does that depend upon? It depends upon the time constant, which is RC. R hasn't changed, C hasn't changed, so therefore T cannot change either. Now the time taken to fall to half of the value, we've learned this before, is 0.69 RC. So you can work it through here, pop in all the values, and you get 0.35 seconds. The next question says, in recent years, supercapacitors have been developed. These components charge and discharge in a similar manner to standard capacitors, but have a capacitance of more than 10,000 farads. They can be used as backup supplies in many circumstances. A 120 farad supercapacitor has an internal resistance of 30 milliohms. At time t equals 0, it stores 30 joules. Calculate the minimum time taken for the capacitor to transfer 250 joules through discharge. Suggest why this is a minimum value. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you would do is you say PD across the capacitor when E equals 30 joules. Well, V is going to equal the square root of 2E over C, because we've just rearranged an equation of the energy stored in the capacitor. So I've rearranged that, I've made V the subject. So we can pop in all those numbers and we get out the value that for that energy is going to have 2.24 volts. So what about when it's at 50 joules? Well, we can work out V again with the same equation, but this time it's going to equal 0.91 volts. So therefore we can work out the time, okay, and therefore we can work that there through. So you can pop in all the values. So when you work it through, you know what V0 is. It's the maximum value, so it's going to be 2.24. We know what V is at that time, 0.91. We can then use the equation V equals V0 e to the minus t over RC. We're going to make T the subject. We know what RC is, okay, when we work it through. Okay, so when we can work it out, we get 3.2 seconds, and this is a minimum value because this is when it has the least amount of resistance, because we're not considering any external resistance, just that input resistance there. The next question says, this question is about charging a capacitor in a circuit with two resistors in series. Firstly, show that the time constant of a circuit is about 15 seconds. Then the graph in figure 2.3 shows how the PD across the capacitor varies with time up to 5 RCs. Add a line to the graph to show how the PD across the 4.7 kilo ohm resistor varies with time. Then add another line to show how the PD across the 2 kilo ohm resistor varies with time. And then calculate the time it takes from the start of the charging for the PD across the capacitor to reach 5 volts. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, time constant equals RC. We know R is going to be the sum of the two resistors in series. We times that therefore by C. C goes from microfarads to farads by times 10 to the minus 6. So RC equals 14.7 seconds. Now you'll see that what happens for the line for the resistor, well, it's going to be exponentially decreasing because it's in series with the capacitor, so it's going to invert what the capacitor does, because as the PD in the capacitor goes up, the PD in the resistor will go down, and it's the same idea for the 2 kilo ohm resistor as well. And then remember, they'll take their potential differences in proportion to their resistances, because that is Kirchhoff's law, which will still be obeyed because this is a series circuit, so you can work it through like so. Then in terms of the time it takes for the charge to work through, well, we're going to have to use our equation that is going to be Q equals Q0 1 minus e to the minus t over RC. We then rearrange it and work it through, okay, and then you can actually, not use the Q version, not the V version of that to work it through. We know that it's going to be starting off at a value of 6, because that is the EMF supply. It goes to 5, so therefore V is equal to 5. We can rearrange it, make T the subject, work it through, and we get 27 seconds out. So Thank you very much for this revision session. If we've been successful and learned in this revision session, we should be able to answer A-level physics examination style questions on capacitors, assess our understanding on the concept of capacitors for A-level physics, and then finally understand what topics you need to improve upon for A-level physics in terms of the capacitance topic. So thank you very much for taking part in this revision session on capacitance. I hope you found it very useful and have a lovely day.